Hello, everyone. My name is Jose Abuan, and I'm here to discuss the problem that our project is trying to solve. The primary challenge is the digitization of handwritten numerical data. While typing is efficient for text, mathematical notation and numerical data are still largely recorded by hand in academic, engineering, and medical settings. The goal is to build a machine learning model that more accurately classifies handwritten digits from images, bridging the gap between analog notes and digital databases. This project serves as a foundational proof of concept for a larger optical character recognition system. Now, who will want to use our product and why? Students and researchers to automate the conversion of handwritten math proofs and data tables into editable LaTeX or Markdown documents. Administrative professionals for digitizing historical handwritten records as ledger entries or census data without manual re entry. Engineers in the field to capture and process numerical measurements from site notes directly into a mobile application. Now, what are our current solutions and why might our machine learning product be an improvement? Now, manual entry is the most common solution in human transcription, which is slow, expensive, and prone to fatigue-based errors. Now, there's also generic OCR like Tesseract. While powerful for standard fonts, generic OCR often fails in the unique variants of human handwriting for varying stroke thickness, slant, and connectivity. Now, the improvement, our product will utilize a CNN specifically trained on the MNIST dataset. While unlike traditional template matching, a CNN is translational invariant and learns spatial hierarchies. This means that it can recognize a form whether it's written thin and tall or short and wide, significantly reducing the error rate compared to non specialized digital tools. So, here we are going to be talking about the exploratory data analysis and our data itself. Before we built the model, we had to dive into the data. We used a standard Kaggle digit recognizer CSVs, even though the data was clean and arrived in a flattened format, basically 784 columns of pixel values. And our first task was to reshape these back into 28 by 28 grayscale images so our convolutional layers could actually see the spatial relationship between pixels. One of the most important steps in our EDA was simply looking at our data. In our notebook, we plotted a sample of these images. You notice that while most digits are clear, there's a lot of variety in handwriting styles. Some sevens have crossbars, some ones are just vertical lines. This variety is exactly why we need the neural network rather than simple hard-coded logic. We also verified the class balance. In a classification task, we don't want to we don't want the model to get lazy by guessing the most frequent number. Fortunately, as seen in our count plots, the distribution across digits 0 through 9 is remarkably even. This means our model has a fair chance to learn the unique variety and features of every single digits. Now that our data is prepped, we move to the baseline model. Think of this as our starting line. We built a standard convolutional neural network because CNNs are specifically designed to understand the spatial hierarchy of images, like how a vertical line and a curve come together to form a six. Our architecture starts with two convolutional layers. These act like a set of eyes looking for specific edges or corners. Between them, we added max pooling layers. These are crucial because they effectively shrink the image, keeping only the most important features. This makes the model faster and helps recognize a 3, even if it's slightly shifted to the left or right. Once the features are extracted, we flatten that data and pass it into a dense layer. The final output is a softmax layer with 10 nodes. This gives us a percentage. For example, the model might say that it's 98% sure an image is 4 and 2% sure that it's a 9. We save this model as a baseline model that Keras, giving us a concrete point of comparison for our later, more advanced versions.
Our first measure of performance of the baseline model was analyzing the training curves based on the training and validation data. The training and validation data did have similar accuracies, although there was slight variance in the validation accuracy as well as in the loss. If we look at the confusion matrix of the initial model, we find that there were some misclassifications. However, we did have great success in correctly predicting the true values of the data. On the right here we have some of the samples of the misclassified images, where we can see that most of this happens to user error of not clearly writing the digits legibly. With our baseline model, we were able to achieve validation accuracy of 99.57% with a loss of 1.64%. This surpassed our initial goal of 98% accuracy, but there were some misclassified images that we believe this model should be able to correctly classify. Our solution to this was to create new models and train them with data augmentation, which essentially takes the data and shifts it around and rotates it to give the model more to train on. We used a total of 3 models, with a baseline, an augmented model, and a slightly less augmented model. After training all 3 models, we then again used the training curve validation to benchmark all of the models. To leverage the advantages of all these models, we ensembled them together and tested different weights on each model using a grid search. This allowed us to achieve a higher accuracy of 99.643% and a lower loss of 1.21%. We were also able to correctly classify images which were previously misclassified. We reduced the variance through tuned weighting averaging, and we added 0 worst cases. The results of the ensembling in the confusion matrix show us that we had less misclassifications, and on the left we have a sample of images that were previously misclassified but were fixed by the ensembling.
Now talking about our simple Flask app. Our simple Flask app just takes all the 3 models that we made and turning into sort of an ensemble and using those models with weights to predict images that you can enter through a user interface. Now, the prepared image takes those images that you uploaded, turns them into a 28 by 28 grayscale, and inputs it to our models. Now, going into our actual app. Now, you see here, we have the actual simple Flask app that is running on localhost. Well, we're going to click on Browse and enter inputs and test and see if it accurately predicts and what the confidence levels are for these digits. We're going to click on Identify Digit, and over here we have the result of 2 at 99.53% confidence level, which is pretty good. We're going to try another one and see how accurate we are. There we go. We have 3 at a confidence level of 100%. Now, these is a pretty simple app right now, and it could be easily used by everybody, but in the future, if we want to make it better for everybody to use, we could create an API that just calls the model and takes those inputs